Hello, I'm Mattheis and I introduce you to my Master Thesis colloquium, Cross-Dating of Intra-Annual Wood Density Series, supervised by Dr. Martin Raden and PD Dr. Hans-Peter Kalle from the Chair of Forest Growth and Dendrochronology. I'll start with an introduction into the topic. Therefore, I'll begin with the general problem I had to solve. Assume you have an old building from which you don't know when it was built, so you don't know the year. And you have wood samples from that building on which you can recognize the different tree rings. Each tree ring corresponds to a year, and my task was now to predict the unknown end year of such a sample to find out the construction year of such a building. And in the following, we will look only on the start years of such samples, which is the same questioning minus the sample length. The current approach for this determination task is this here. In the first step, we extract the maximum densities from such wood sample here on the top. So here in this diagram below, we have on the vertical axis the maximum density of these points here, and on the horizontal axis we have the years of the points. And in the second step, this sample has to be now compared against such a master chronology of known years, which was built by averaging such samples with known years. But now, how does the determination task works? Therefore, we have to compute the t-values or correlation coefficients between such red marked curves, and this for every start year. So here we compute the correlation coefficient for 1916 as the start year, here for 1917, 18, 19, and so on. This finally leads to this table here. So here on the top we have the years, and here the corresponding correlation coefficients below. And now these years are sorted depending on their correlation coefficient. So here in a descending order. And 1992 is now the most probable solution, 1996 is the second most probable solution, and so on. So each year gets a rank. And now I've generated a test set with 250 length 10 samples. So each of the test samples had 10 measuring points and a start year, as you can see. And I have now predicted the correct rank for that start year. In this table, and here I make now an example. So this sample from 1996 in this left bottom table is the one which was shifted on the last slide along the chronology. So the corresponding table of scores we see here at the top. And 1992 we see has as predicted rank 1, 1996 has the predicted rank 2. So this is how we come to this 2 here in this bottom right table. And now remember that headline, predicted rank of a start year, because you will see this headline again and again throughout the presentation on the horizontal axis of frequency diagrams. Also here on the next slide. So here on the horizontal axis, it's predicted rank of start year, and on the vertical axis we have the frequency of these ranks. And what we can recognize here is that 112 out of 250 samples were ranked correctly, so about 45%. And about 77% were in the top 5. So overall, this approach does not work good for short samples like length 10. Today, it is said that at least 25 rings are necessary to get reliable results. But we can do it better by using so-called intra-annual data we get, for example, from density profiles. So this was my goal, to create a new, more precise procedure which works for short sample lengths and with the help of density profiles. So instead of ring widths or maximum densities, we now extract density profiles from the rings. So here on the vertical axis again the density, and on the horizontal axis the years. And such a sample is now compared against a master chronology of known years, in this case here a consensus chronology. This is done again via sliding window approach. Okay, now how does this consensus chronology is built? This you can see here on the next slide. That's the data I get from my supervisor, Dr. Martin Raden. So I get the density series from 56 Norway spruces from the Swabian Ostalb in Germany. And I have built a consensus chronology by using a program which was developed here called Mika. Here you see what Mika does. It first aligns characteristic points like minima, and then it builds the average. The idea behind this is that you want time synchronous data. So monthly events like drafts should be realigned again before you build the average. Okay, you have now seen what is a chronology and what are density series. Now let's look on a few approaches I have implemented. The first one was the consensus approach. We have here again at the top the years, and here the consensus below, and then a test sample from 1964, just as a random example. And we do now a profile-wise comparison. So we compare this first two profiles and get a distance. We compute the next two, get a distance. And finally, all distances are summed up to get a final distance for 1916. The same is repeated for 1917, 1918, 19, and so on. So we get again such a table. And now we sort the years depending on the reached distance. This times in an ascending order because we're using distances and not correlation coefficients. And 1992 is now the most probable solution, so the most probable start year. 1996 is the second most probable start year, and so on. And on the last slide I said that the test sample was from 1964. So let's look up the predicted rank. We see the predicted rank for 1964 is 3. And why I show you this? Because on the next slide we have again such a histogram. And yeah, for this histogram I have extracted the corresponding density profiles for the maximum densities which were used before. And what we recognize is that there was a worsening. So only 32% were ranked correctly. Here, a direct comparison with the maximum density approach. But why is this the case? We use much more information. So density profiles contain much more information. Here's the answer. If you look on the individual profiles from which such a consensus profile was built, so here on the right side, then you see many different curves. So the consensus does not represent well enough the curves from which it was built, so you lost information. And to avoid such information lost, the bucket approach was created. The idea of the bucket approach is that you do not use anymore a single profile, the consensus. You use the individual profiles from which it was built. So here on the left side, these profiles you use. And then you put them all in buckets and get such a buckets chronology. Now let's do the comparison. We compare against the first profile in the bucket, get some distance. Compare against the second, get a distance. Compare against the last one and get again a distance. And finally we choose out of all these distances the minimum. The same is repeated here. We compare against the first, we compare against the second, and finally we choose the minimum. Okay. We choose here again the minimum, and finally all these minimum distances are summed up to get a final distance for 1916. So the idea behind this bucket approach is that you choose the most similar profile in a bucket and build with that the distance. So there was a mathematical intuition behind. It was not a random discovery. And here are now the results. I've used again the same test samples as before, but this time I had about 59% correctly rated test samples. And about 78% were in the top 5. Here a direct comparison with the maximum density approach here in green. And also here the consensus approach. We see we outperformed the consensus approach here in the top 2 for rank 1 rated samples and rank 2 rated samples. It has been outperformed. But this bucket approach was comparatively slow. So for 250 test samples, about 20 minutes were necessary, and compared to the maximum density approach, there you need only 3 seconds. Okay, there was a new problem. Now, how this new problem was solved? The new problem was solved with the 2-step approach. The idea of the 2-step approach is the maximum density approach is very fast and the bucket approach is very accurate. So let's combine both approaches to an overall fast and precise algorithm. Now, how does the combination works? Therefore, you first execute the maximum density approach, as shown before. So for each start year, you compute a correlation coefficient, here for 1916, then for 1917, 18, 19, and so on. And then you return the start years with the highest correlation coefficients. So this red marked years here. And for this start years, you now extract the corresponding windows of buckets of length 10 and execute the bucket approach only on these windows. So the idea is that you limit the number of years which should be executed by the slow bucket approach. And by this you get that results here. So we had even a side effect, and the side effect was a higher number of correctly rated test samples. Now 70% were ranked correctly, and about 84% were in the top 5. Here a direct comparison with the bucket approach. So we had an improvement by 11%. And the runtime was also better, as I said. So 50 samples in the bucket approach needed about 4.5 minutes, and in this new two-step approach only 1 minute and 17 seconds on average. Finally, I made an overview with the runtimes and the length dependency of the different approaches. We have seen how stepwise the new algorithm, the two-step approach, was developed. And it has now some advantages and disadvantages compared to earlier methods like the maximum density approach, and exactly this should be now summarized on that slide here. Here on the left side we see the different approaches, the maximum density approach in green, the consensus approach in red, the bucket approach in blue, and for this two-step approach we use this violet. And here on the right side we see the corresponding diagram for the runtimes in seconds. So on the horizontal axis I mapped the runtime in seconds, and on the vertical axis I mapped the approach. And what can be recognized directly is that this maximum density approach, it is much faster compared to the other approaches. Especially this two-step approach would be in a runtime ranking only on the 3rd place, as can be seen here. It is about 130 times slower, but therefore it is much more accurate than the maximum density approach. So here in this length dependency diagram I tested for different sizes of the test samples. So I've used length 1 samples, length 5, length 10, and length 15 test samples, and mapped the number of correctly rated test samples on the vertical axis in percent. And if we compare here now for length 10, the maximum density approach and the two-step approach, then we see the two-step approach has reached about 70% correctly rated test samples, as said before, whereas the maximum density approach reached only 45%. So there was an improvement by about 25%. And this curve of the two-step approach was always above the curve of the maximum density approach. But the distance, so the difference, it became smaller for longer test sample sizes. This can especially be seen here in this next plot. There I have shown the number of top 5 rated test samples. So for the top 5 ranks. And yeah, we start in the maximum density approach with about 50%, this green curve for length 5, and end up with 95% top 5 rated test samples. So the maximum density approach has even outperformed the two-step approach on the top 5 for length 15. So we can conclude that currently there's nothing better than the two-step approach for short sample lengths like length 10 and below, but for longer test sample sizes there exists already a fast and precise algorithm. However, I had to develop a new, more accurate method which works for short sample lengths, and there I think I have succeeded. Thank you for your attention. Here you see now the practical part to my thesis, the cross-dating project, so the R implementation, which you can find on the Bioinformatics Lab. This you can find on github.com, Bioinformatics cross-dating. And here you have just to download the zip file. And then you just extract these downloaded files and place them in your R projects folder, which could be under documents or anywhere else where you've created that R projects folder. Then you switch to RStudio and you go into that cross-dating folder you've downloaded and extracted and set it the working directory. And now this main.r script contains everything you need to execute the approaches. Here's an interface function which you can find here below. It contains pre-defined functions, and so I've computed some files in a special encoding, which you also can see here on the Bioinformatics Lab. So if you go here, then you see what the input files look like I've created for you already, and you see also how the output files will look like if you execute one of the approaches. But to execute one of the approaches, you have first to install some of the libraries you see here. You have just to execute first this command here. So let's copy that. And this you enter in the console, and then it will install the necessary libraries to execute the interface functions you see here. As long we can copy the next command here. Our Java has to be installed too, because Mika needs this. So there's a program called Mika, and this needs Air Java, the Air Java package. Okay, this was done. And now you just uncomment an approach with Control-Shift-C, and now with Control-A you select all and press Control and the Enter key, and then it will execute here for you the approach. So in this case the consensus approach, because it is started here above. So the first function which is started is the main function, and you see main.interface is not uncommented. So in the main interface function the consensus approach will be executed. And you see it's done. You have also seen that output, which shows you that that program is working. Okay, that was all. You have seen how you execute an interface function, how you install everything. Here on the output folder you see also the data, so everything what's computed with the interface class, it's stored in the output folder of this cross-dating project. And here you find additionally other libraries which are necessary to execute my experiment. So if you want compute some visualization, you can execute here the experiments. Okay, thank you for watching.